What if I told you that you've never really seen a rainbow? At least not in the way you probably think. That giant, majestic arc of color we see painted across a rainy sky isn't some massive object that everyone shares. It's a private, personal illusion, created just for you. It's an experience so unique that no two people in history have ever seen the exact same one. Not only that, but even your own two eyes are seeing different rainbows. Sounds impossible, right? A rainbow feels universal. We point at it, we take pictures of it, we all agree it's there. But the truth is far stranger and, frankly, more beautiful. The rainbow you see is an optical phantom, a personal light show built from a perfect, unshareable alignment of the sun, billions of raindrops, and the precise position of your eyes. So let's unravel this beautiful mystery. We'll look at how light works inside a single raindrop, and then we'll see how our own minds perceive it. By the end, you won't just understand why your rainbow is yours alone. You'll see the entire world and your place in it in a completely new light. For as long as we've been human, we've looked up after a storm and seen the rainbow as a powerful, unifying symbol. It's the Bifrost Bridge in Norse mythology, connecting mortals to the gods. In Judeo-Christian traditions, it's a divine promise. In countless cultures, it's a sign of luck, hope, and new beginnings. There's something in us that feels the need to share it. A shout of, "Look, a rainbow," makes everyone turn their head to the same spot, and we all gasp at the same brilliant display. It feels like a show put on by nature for everyone to see. We think of it as a physical thing, something with a specific location. It appears over there behind that hill, or seems to end in that field. This leads to the timeless myth of a pot of gold at the rainbow's end, a quest that's captivated kids and dreamers for centuries. The logic makes sense. If it's an object in a specific place, you should be able to get to it. This idea of the rainbow as a static, shared landmark is one of the most powerful illusions we experience. We treat it like a mountain on the horizon, something that exists independently of us. We take a photo and assume the person next to us is seeing the very same image we are. But this is where our intuition leads us astray. Every one of these assumptions, that it's a single object, that it has a fixed location, that it's a shared experience, is wrong. To understand why, we need to stop looking at the whole arc and instead focus on the three ingredients that create it: the sun, the water, and most importantly, you. To create the perfect rainbow, you need a precise recipe. The first ingredient is sunlight. But what is sunlight? We see it as warm, white light, but that's a trick. Sunlight is actually a cocktail of every color imaginable. It's a flood of photons traveling 93 million miles from the sun, each vibrating at a different frequency. A tiny slice of this spectrum, from the long, lazy waves of red light to the short, energetic waves of violet, is what our eyes can see. When all these colors hit our eye at once, our brain mixes them together and calls it white. So ingredient 1 isn't just light, it's a hidden spectrum of color. The second ingredient is water, specifically tiny, suspended droplets of water, like the mist after a rain shower. And their shape is incredibly important. Thanks to surface tension, small raindrops aren't teardrop-shaped. They're almost perfect spheres. Think of them as billions of tiny glass marbles floating in the air. This spherical shape is critical. It turns every single raindrop into a miniature prism. And the third and final ingredient is you. This is the part we usually forget. We think we're just passive spectators, but you are as essential to a rainbow as the sun and the rain. More specifically, the exact position of your eyes completes the recipe. A rainbow simply doesn't exist without an eye, or a camera lens, in the right place to see it.
So, we have our ingredients: a hidden spectrum of light, billions of tiny spherical water lenses, and an observer. Now, let's see what happens when they all come together. Let's zoom in on a single, solitary raindrop. A ray of white sunlight, carrying all its hidden colors, hits the surface of this droplet. As the light passes from the air into the denser water, it bends. This is called refraction. But here's the magic. Not all colors bend by the same amount. This is called dispersion. Violet light, with its shorter wavelength, bends the most. Red light, with its longer wavelength, bends the least. The moment sunlight enters the raindrop, the white light shatters, fanning out into its component colors, just like light through a prism. Now, this separated spectrum of colors travels through the droplet until it hits the back surface. Here, some of the light reflects, bouncing off the back of the raindrop like a curved mirror. This internal reflection sends the now separated colors back toward the front. As these colored rays travel back to the front to exit the droplet, they have to pass from water back into the air. So they refract again, bending once more as they exit. This second refraction spreads the colors out even further, amplifying the separation. The result of this three-step dance, refraction, reflection, then refraction again, is that a single ray of white sunlight emerges as a brilliant fan of colored light. Every single raindrop hit by the sun is doing this, acting like a tiny natural projector, casting a miniature spectrum of color. You are standing in a sky filled with billions of these microscopic projectors. But if every raindrop projects a full spectrum, why don't we just see a blurry white mess? Why do we see a perfectly ordered, giant arc of distinct colors? The answer lies in a very precise rule of geometry. This is the key that unlocks the whole thing. The light that emerges from the raindrop doesn't just scatter randomly. The physics of the spherical droplet concentrate the light at a very specific angle. For red light, the angle between the incoming sunlight and the outgoing red light is about 42 degrees. For violet light, which bends more, that angle is smaller, around 40 degrees. Every other color has its own magic angle in between. Think about what this means. You're standing with the sun directly behind you. To see the color red from a particular raindrop, that drop must be in a position that forms a perfect 42-degree angle between the sun, the droplet, and your eye. If a droplet is at a 43-degree angle, its red light will fly right over your head. If it's at 41 degrees, the light will hit your feet. The only red light you can see comes from the entire collection of raindrops that happen to sit on that perfect 42-degree cone of vision extending from your eye. The same goes for all the other colors. The raindrops that can send you violet light must be on a slightly lower 40-degree cone. The drops sending you orange light are on a cone just inside the red one, and so on. What you perceive as a rainbow isn't one big thing. It's a composite image made from billions of individual droplets. The red stripe you see is made of one set of raindrops, all perfectly positioned at 42 degrees from your line of sight. The orange stripe you see is made of a completely different set of raindrops, all at around 41 degrees. Each droplet contributes only one single color to the rainbow that you see. This is why a rainbow is an arc. You're just seeing a slice of a massive circle. The full circle of light exists, but the ground usually gets in the way. The center of the circle is a point in space called the anti-solar point, and here's where it all comes together. So where is this anti-solar point, the center of your rainbow? It's the point in space directly opposite the sun from you, and there's a really simple way to find it. Look at your own shadow. The anti-solar point is always located right at the shadow of your head. Let that sink in. The center of the rainbow's arc is anchored to your specific point of view in the universe. Now, imagine standing next to a friend. You're both looking at the same amazing rainbow. Since you can't occupy the exact same space, your heads are in slightly different locations. Therefore, your shadows are in different places. Your anti-solar points are in different places.
This means the 42-degree cone of red light entering your eye is coming from a completely different set of raindrops than the one entering your friend's eye. You are seeing your rainbow, and they are seeing theirs. They might look almost identical, but they are physically distinct. The rainbow isn't a shared object, it's a shared event, and your experience of it is completely unique. It gets even stranger. The uniqueness isn't just between people, it's within you. Your left eye and your right eye are a few inches apart. Because of this, your left eye sees a rainbow made by one set of raindrops, and your right eye sees a slightly different rainbow made by another set.
Your brain, being the amazing processor it is, seamlessly stitches these two personal rainbows together to create the illusion of a single, stable arc. The rainbow you see isn't just personal to you, it's personal to each of your eyes. It isn't an illusion because it's fake, it's an illusion because its very existence depends on the observer. If you try to walk towards it, the angle changes. As you move, your anti-solar point moves with you, and the set of raindrops creating the illusion constantly shifts. The rainbow will always appear to be the same distance away, forever out of reach. There is no pot of gold because the end of the rainbow is an optical projection, not a physical place. But the uniqueness doesn't stop there. It goes one step deeper, from the outside world of physics to the inner world of your own biology. Even if, by some impossible miracle, the exact same photons from a rainbow could enter your eye and your friend's eye, you still wouldn't see the same thing. Here's why. When that red light enters your eye, it hits the retina, which is covered with light-sensitive cells called cones. Most of us have 3 types of cones, for short, blue, medium, green, and long, red, wavelengths of light. When red light from the rainbow hits your retina, it mainly stimulates the red cones. Your brain then gets a storm of electrical signals and interprets this as the experience of seeing red. But the exact sensitivity of your cones isn't the same as anyone else's. Thanks to tiny genetic variations, the ratio of your red to green cones can vary dramatically from person to person. Some people have way more red-sensitive cones, making them great at spotting differences in the red-orange part of the spectrum. Some women, known as tetrachromats, even have a 4th type of cone, allowing them to see color variations that are completely invisible to the rest of us. Beyond the hardware of the eye is the software of the brain. Your personal history, your memories, even the language you speak can influence how you categorize color. The classic 7-color rainbow, red, orange, yellow, green, blue, indigo, violet, is mostly a cultural convention started by Isaac Newton, who chose 7 because it was a mystically significant number, like the 7 notes of a musical scale. There are no hard lines in a real rainbow. It's a continuous spectrum. The boundaries you see are being drawn, in part, by your mind. So your experience is doubly unique. First, you're the only one seeing a specific pattern of light rays centered perfectly on you. Second, you're filtering that unique light through your own unique biology and brain. This core idea, that what you see depends on your angle, unlocks other cool optical tricks. Ever see a double rainbow? That fainter, second arc higher in the sky, with its colors reversed? That's caused by light that makes 2 internal reflections inside the raindrops before exiting. This second bounce sends light out at a higher angle, around 51 degrees, creating a second personal rainbow just for you. That dark patch of sky between the 2 rainbows even has a name, Alexander's Band. It's darker because raindrops in that region are reflecting light away from you.
And while you can't reach the end of a rainbow on the ground, if you're high enough, in a plane or on a mountain, you can sometimes see its true form, a full, spectacular circle. With no ground to block the view, you can see the entire 360-degree cone of light, always centered on your plane's shadow as it races across the clouds below. Even on a bright moonlit night, the same physics can create a moonbow. It's often too faint for our eyes to see the color, so it usually looks like a ghostly white arc, but it's a true rainbow, centered on the point opposite the moon. So that magnificent arc in the sky isn't an object or a place, it's a relationship, an exclusive one between the sun, countless water droplets, and you. It is a halo of light centered on your own shadow, a crown that only you can truly see. The rainbow is a profound paradox. It's a universal symbol that connects us, making us all stop and look up in wonder. Yet the image itself, the actual light entering our eyes, is one of the most private experiences in nature. Millions can witness a rainbow, but each one sees their very own. It's a beautiful metaphor for consciousness itself. We all live in the same world, under the same sun. We share experiences and we connect. But ultimately, we each view that world from a unique perspective,
We can point to the same beauty, but we can never truly see it through another's eyes. So the next time you see a rainbow, cherish it. Know that you are seeing a fleeting personal miracle, a spectacle created by the universe for an audience of one. If this has changed the way you see the world, even just a little bit, please like this video and share it with someone you'd want to share a rainbow with, even if you now know that's impossible. For more dives into the hidden wonders of our world, make sure to subscribe. Thanks for watching.